In this video, I'll be talking about reflection, refraction, and diffraction of water waves. It's part of topic 4.4 in the IB Physics Syllabus, so that means it's relevant to both SL and HL students. Please take a moment to read the success criteria for this video. So first, let's just remind ourselves of what can happen when a wave hits a boundary. There are three possible things that can occur. It can be absorbed, it can be reflected, or it can be transmitted, which means it'll travel from one medium to the next. So in my diagram here, first of all, I have the incidence or incoming wave. I have here wave fronts. So this is showing my wave in 2 dimensions. And we talk about the direction of the wave being perpendicular to the wave fronts, and we could call it this a ray. If I was just talking about light, we typically only talk about a ray of light. So there's my incident ray, and you can see here that it's being reflected. If you remember from before, we always measure from this dotted line here, which is called the normal. We call it that because it is perpendicular to the surface. So just like in math class when you have a normal there. No matter what the surface is like, rough or smooth, we can always get a normal at that point on our surface. So my top diagram here is just to remind us what I mean by a wave front. For example, I've got the blue lines here, which would be the peaks or the crests of my wave. And so we're looking at our wave moving along in this direction, whereas here's my wave front perpendicular to that. The other thing about thinking about this is we can then, from our diagrams, measure our wavelength, which would be the distance between those two wave fronts. We use water waves a lot, especially when we go from shallow water to deep water because the speed of the wave changes. But we could also talk about waves going not just from one medium to another, but in my diagram down below, you can see that I've got a thin rope here to a thick rope. That's, in this case here, my wave will travel much faster through my thin rope than it will through the thick. One thing to remember when a wave travels from one medium to another is that the frequency will not change. The frequency is how the particles, in this case a transverse wave, are being forced to move up and down. So it's the frequency at which they're being moved up and down. In this direction, that's how fast that the energy can be transferred from one particle to its next particle. That is due to the medium it's in. So when we get to a second medium, the frequency of which it's being oscillated will not change, only how fast it can pass on the medium. So what does this mean? It means with our wave equation, velocity equals frequency times the wavelength. If I'm telling you now that the frequency doesn't change, if my speed increases, that means my wavelength will also increase. If it slows down, then my wavelength gets longer. So most people in middle school saw that the angle of incidence equals the angle of reflection for a light ray. But the same thing's going to happen with your plane wave in water. Plane as in 2 dimensions, like in math class. So we've got here this line. You can see it's about to come to the boundary. What I have here is that this bottom part of the wave has already hit the wall and is starting to reflect, where this part of the wave hasn't hit it yet. If I have my normal drawn in, you will actually see that this angle here will equal the reflected ray. And as this wave continues to move on, then we'll have more of the wave front that's reflected and some that has not. We've got a couple of really good places here that you could go look at this. I have down below on the right, I have a snapshot of a YouTube video from St. Mary's University called Reflection of Waves. It's a nice little short video of about 30 seconds long, and you'll be able to see these plane waves coming in and bouncing off this surface. You can see here my plane waves, and this line here is the reflected wave fronts. Another thing you could do is go look at the ripple tank simulation at this website here, and you can also play around with how you can see this reflection of plane waves off of different surfaces. So let's talk more about the transmitted wave. So now we're talking about refraction, not reflection. So when my wavefront comes into my boundary, you can see here that this red line hasn't quite hit the boundary yet, but a little bit farther along. Now this part has not hit the boundary, but this part has. Now let's think about what's actually happening there. I'm going to use this green line here to help us look at this. So as my wave is coming forward, what's happening here is, if it was here, my line should have been way down here, but it's not. What does that tell me is going on? This medium must be slower. And that's why we have this part of our wave kind of lagging behind where it could have been if it didn't actually pass through this boundary. And you can see that very clearly right here. We have that this part of the wave is still traveling. In my case, I've said it's air. And down here, all of this part of the wavefront is lagging behind. So what does that end up doing? It ends up causing my wave to change direction. We used to be going at this angle, and now we're going at this angle. Remember, the direction of the wave is perpendicular to the wavefront. How do you think we're going to measure what angle it was before and after? Of course, we need a normal. Okay, and in this case, we can see here, we could call it theta 1 for my incident angle, and then this one here will be theta 2, which would be for the refracted angle, or angle of refraction. We can see that when we go from a medium where the wave is traveling faster to a medium where a wave is traveling slower, we say it bends towards the normal. If I would draw a straight line with that ray, you can see if we didn't go from one medium to the other, it would have still continued straight on and at this angle. But since we have it changing directions or bending as it goes from one medium to another, refracting, we can see that it's bent towards the normal. Likewise, if we went in the opposite direction, it would have bent away from the normal. One thing I want to point out is this picture over here, because a lot of the times we'll use a rectangular prism. And in this case, you can see that we have an incident ray. It's going to hit the edge, and it's going to bend, again, in this case, towards the normal. Now, these two edges are parallel. So in this case, it's going to then hit the next boundary, and it's going to be bending away from the normal. Now, however amount it bent towards the normal on the first boundary, it's going to have to bend that same amount back in the second boundary. So what you end up getting, because the edges are parallel, is that the incident ray and the transmitted ray here are going to be parallel, but they are offset due to the refraction in the center. Now, with all of this, if we put it in, we've got this equation. It's so famous that we still call it after the guy's name, Mr. Snell. Thank you very much for doing all this work for us. We have N1 over N2. N is an index of refraction, and that is taking the speed of light in a vacuum and dividing it by the speed of the light in the medium and giving us a number. Because the speed of light is always at the top and it's the fastest it can travel, this number always must be greater or equal to 1. For those of you in chemistry, do not confuse it with calculating a molar concentration. Okay, so let's take a look what happens when we go from a more optically dense medium to a less optically dense medium. Please don't get it confused with density as mass over volume, because that's not what we're referring to. We're referring to a higher index of refraction, or refractive index, to a lower index of refraction. I said in the previous slide that it was going to bend away from the normal. So here we go. We've got this black line and we come to a boundary from a high optically dense to a lower optically dense. And if it had gone straight through, we would have gone here, but instead it's bent away from the normal. At some point, though, there's only so far it can bend away from the normal. And if my refractive angle is 90 degrees, that is the last chance I'm going to have for a refractive ray. We call the angle of incidence so that my angle of refraction is 90 degrees, the critical angle. So if you have anything that's beyond the critical angle, then, well, it's not possible to refract farther away from the normal than 90 degrees. So what you end up having is total internal reflection. Notice it's reflection, not refraction. And because of that, my angle of incidence here will equal my angle of reflection. So you can see here my question, why do so many experiments use this semicircle or half circle prism? And that's due to the properties of a circle. If you aim a ray directly towards the center of the circle, what that means is right here, you will always be hitting this along the normal. If that's the case, if your angle of incidence at this boundary here then would be 0, there is no refraction. So we will only get refraction at this edge. Likewise, if I had a light ray coming in from the other edge, and I have it hitting my boundary here, it's going to bend towards the normal. When it will then leave my circular or semicircular prism, because I'm going through the normal, I do not get any refraction at this edge. So that's why they're used. We can do our experiments refraction and actually have it happening at only one boundary. Okay, so let's talk about diffraction. Now, these words are starting to sound very similar, but it's very important you keep them separate. Diffraction is a wave coming to either an opening, like you see I have here, or it could be going around an obstacle. But it's when a wave then will change its direction after going through the opening. So, a couple things to point out of what's happening here. First of all, let's talk about all those things that are the same. See how these lines are equally spaced before and after? That means my wavelength has not changed. We said before that the frequency is due to the disturbance. That's not going to change. So therefore, since my wavelength hasn't changed, my frequency hasn't changed, neither has my speed. What will happen though is it starts to bend around. And if you haven't read it, and please forgive my pronunciation, but the guy's name is Huygens. He is Dutch, so thus my bad pronunciation. But if you want to know more about why this occurs, you can read up about him. It's no longer in the IB syllabus. So as we go through, if I want to get this effect of it bending around, then you can see in our first diagram here, we don't have much bending occur. But in the second one we do, and we get like this cone being created afterwards. And I will get the most obvious diffraction here if my gap is about the same size as the wavelength. One thing that will be important to realize is, in this case, my wave is just over this amount of area. As I get farther and farther, that power is going to have to go over a larger and larger area, and it will decrease in amplitude. So let's go through a few different multiple choice examples. Okay, so when it goes from air to glass, which one of the things happens to the frequency and the wavelength? Make sure to pause the video and try it out first. Okay, one good trick about doing questions like this is to look at the columns first. Frequency, we know it stays the same, so I'm going to get rid of decreases. Wavelength, now from air to glass, it's going to slow down, and that means since the frequency is the same, the wavelength should decrease. So let me get rid of the wrong answers. So the only one that's left that could be possible is A. Okay, so we've got some wavefronts here going from shallow water to deep water. Now, if you don't remember, this is what's going to happen. It's slower in the shallower water. Think of it as the bottom causes extra friction compared to the deeper water. So pause the video, read the answers, and make your choice. Okay, so right here, this is going to be reflection. So we'll look at our list, and I have reflection, yes, and yes, and yes. So the other thing is what's happening here? And this part is going to be refraction. So again, let's go and find refraction and refraction. So the only one could be D. Let's take a moment and think about the ones we didn't circle. Diffraction. Remember, that was how waves are changing when they go through an opening or around an obstacle. And dispersion, that's when you take white light and you create your rainbow, your spectrum. Okay, so let's talk about our opening here. Diagram 1 has a ripple tank in which the plane waves are diffracted through a narrow slit, and the same one in the diagram 2, but the opening is greater. So what action would cause the waves in diagram 1 to be diffracted less and produce a pattern closer to that of diagram 2? Make sure you pause and think about it first. Okay, so let's take a look at getting rid of some of these that aren't going to make any sense for us. First of all, with C, reducing the amplitude of the vibration, that has nothing to do with the diffraction pattern, so let's get rid of that. Likewise, the length of the vibrating bar is not going to affect the pattern that I have, assuming that it's at least the width of the opening. So that leaves me these last two, increasing the frequency of the vibration bar. So if we think about it, what will that do? That will decrease my wavelength. If I increase the speed of the waves by making the water deeper, that's going to increase my lambda. So then, how am I going to get this to occur? Remember, if the wavelength is smaller compared to the opening, that's what I have in diagram 2. And we can see here with the small wavefront compared to the size of the opening, then I don't have very much diffraction. So what do I need in this case? I need to have A. Okay, so which one of these, A, B, or C, or D, could be the possible path of the light of my wave at this boundary? Pause and think about it. Okay, hopefully can't be B because we're definitely going to have refraction. So now let's look at the other ones. Either in A, we have that the light's coming in and it's bending away from the normal and then back towards, or C, we have it bending towards the normal, then away. Oh, there's no possible way it's going to happen here at D because we know that if it is at 90 degrees to the surface, i.e. it's along the normal, no refraction occurs. So now we're back to A or C. So if you remember air, and to be honest, I think of it easiest as a wavefront. I know from air to glass it's going to slow down. So if I have my wave here, this one's going to be in this direction. What has it done? It's bent towards the normal. So my answer is going to be C, not A. And one more about refraction and critical angles. So here's that semicircular glass again. Now, depending what that angle I is in reference to the critical angle, we could have some different scenarios going on. So, stop, pause, read the answers, and come up with an answer. Okay, so I'm going to start by drawing a couple of rays in here to help me out. So let's say that this ray here is going to be my critical angle. So if I then have this one here and it's not at the critical angle, then I am going to get some refraction. If I have another one and it's greater than the critical angle, I'm going to get total internal reflection. Now, there's a few other things we've got to point out here, and that is with this green line, even though it's being transmitted, I actually will always get reflection. I'll just get a small amount of it. Now, think of it this way. If you look at a piece of glass and it's dark outside, you see your reflection. If it's daytime outside and it's really bright, you don't see that reflection. That doesn't mean it's not there. It just means that in comparison to the other light coming through, you don't notice it. Okay, but at the boundary, there will always be some reflection. So let's look back at these statements. When I is bigger than C, no light is reflected. Incorrect. It's all total internal reflection. When I is bigger than C, no light is transmitted. That's true. There is no refraction. When I is smaller than C, no light is reflected. Not true. When I is smaller than C, no light is transmitted. Not true. Well, I hope if you read the success criteria, you can now answer yes to all of these statements.